Okay, last class we had a brief introduction to trigonometry, and we talked about radian measure and degree measure and what? Coterminal angles, supplementary angles, complementary angles, and all those sorts of things. And we talked about that dealing with radians, and we talked about that also with dealing in degree mode. And we talked about how to convert from radians to degrees, from degrees to radians. Well, we're going to start today off by talking a little bit more about degrees, okay? If you remember, or if you think back, we may have some decimal part, maybe like 25.75 degrees. And we want to know, what that comes from. You may have heard the term degree, minute, seconds, okay? We're going to learn how to get the fractional parts of degrees and express them as degrees, minutes, and seconds. This is not very widely used, but we are going to introduce it to you because you may see some things that you have to put in degree, minute, and second mode. If you have a scientific calculator, it should have that on there somewhere, okay? So let's talk about degrees, minutes, and seconds. We know about degrees. That fractional part, as I said, 25 degrees, 0.75. We need to talk about what that 0.75 means. We need to talk about what 1 minute is. One with the little, I can't think of what that's called, English people. What's that called? Apostrophe. There you go. This represents 1 minute. And 1 minute will be represented as 1/60th of a degree. Okay? 1/60th of a degree. Quotation marks. I remember that one. If you have one in the quotation marks, this represents 1 second. And the equivalence here is 1/3600 of a degree. So we're going to use these equivalences here to convert to degrees, minutes, seconds. For example, if we have something like 64 degrees, and we'll write it out, 64 degrees, 32 minutes, and 47 seconds. This is written 64 with a degree mark, 32 apostrophe mark, 47 quotation mark. 64 degrees, 32 minutes, 47 seconds. Now, how do I translate this into something with a decimal? Okay? How do I translate this into something with a decimal? Well, we want the 64 degree portion. What we're going to now do is have our 32, and we'll put it as what? Maybe we should say this a little differently to follow suit with what we have on the board. But we should say 32 times our 1/60, our 1 degree here. Because here, this is how we translate the minutes, by this 1/60 times 1 degree, plus our 47 times our 1/3600 times our 1 degree. So for this, we need a calculator, okay? For this, we need a calculator. What this translates to is if you have 64 plus 32 divided by 60 plus 47 divided by 3600, then you should get what this is in decimal form. You should get 64.5464 degrees. Okay? So for our minutes, we put the minutes over 60, attach the degree symbol. We put the seconds over 3,600 and attach our degree symbol. And then we use our calculator to get that approximation here. Okay? So this portion represents the decimal portion. So really 64, you really want to get what goes after the decimal. You do 36 over 60 plus 47 over 3,600, and that should give you this 0.5464. Okay? And as I said, this is not widely used in trigonometry. You may see a problem scattered here or there throughout trigonometry where you have this degree, minute, and second, but not many. Let's look at another problem, converting to decimal mode. Suppose we have 245 degrees and 10 minutes. Okay? So, again, our 245 degrees plus our what? We can do 10 over, since we're doing minutes, 60, and attach our degree. And what this should get, we should have our 245. This tells me what goes after the decimal, and we should have 1.167 degrees. Need to make sure that we put our degree symbol there. Because what happens if we don't have a degree symbol? What are we assuming? We are assuming radians. Remember, if you don't have that degree symbol and you just have something here with just a number, it is assumed to be radians. Now, how do we convert the other way? Suppose we have something in decimal mode and we want to convert to degree, minute, second mode. That's our abbreviation. Degree, minute, seconds. And suppose we have 0.355 degrees. And this has a negative attached. Negative 0.355 degrees. Well, this whole number portion tell us what? What goes on this side of the decimal. So we know we're dealing with 0 point something degrees. We need to convert this to, it's going to be negative 0 whatever degrees. We have to find out the minutes and the seconds. So how do we find out the minutes and the seconds? Well, I take this negative, and I can put that negative outside, 0.355, and I want to multiply it by by 60. Okay? If I multiply that by 60, let's see what we get on. I brought my calculator today. If I multiply 0.355 by 60, then I get what? 21.3. But I'm going to use that 21. We know it's 0 degrees. I'm going to take the whole number portion, and that's going to be my minute portion. Does that make sense? Okay? 0 degrees. I know it's going to be negative 0 degrees. I do 0.355 times 60. I get 21.3, but I take the whole number portion, and that will be my minute. Now I need to find my seconds. What was my decimal? 0.3, right? So now I multiply, I add this 0.3 again times 60. And you're probably saying, okay, why do I do times 60 here, times 60 there? Well, that's because we're breaking this up, going with minutes, then seconds, okay? 60 times 60 is what? That 3,600 that we will have there. But since we're breaking it up and we're using these fractional parts, we're going to multiply by 60. So now I have negative 0 degrees 21 minutes. And now I need to figure out what this portion is. 0.3 times 6, 60, 18. So I have negative 0 degrees, 21 minutes, 18 seconds. Okay? And as I said before, this is not that widely used. We're not going to spend a whole lot of time on this degree, minutes, seconds, okay? Okay, the question was, why did we use this 60 here? If we had, from this point, wanted to convert all of it at one time, we would have probably used just the 360. But we're taking it step by step, using here when we do the 0.355 times 60, we're taking that whole number portion, and we're using it as our what? Minutes. And since we multiply by 60 here, we want to go on down and do the 60 here with the 0.3 that was left over. You're still multiplying by, what, 3,600. You're just breaking it up. This seems to be a little bit easier, because if you do all this with 360, then you won't know, well, what portion is what. You know, it's easiest to break it down. 1 second.
The answer to that was the 21 was a 21.3.
Right, and you use the 21 minutes.
So then you use the next decimal.
Then we do the 0.3 times 60.
I was just on the top, when you first divide or multiply by 60, don't read you multiply down the bottom because you have to use the same thing?
We're doing a total of 3,600, and we're breaking our 3,600 up into 60 times 60. Okay. And it makes it easier to think about.
Okay, all right.
Okay? So we want to break it up into 60 to get our minutes, and then this 60 to get our seconds, but it's still, what, 3,600. Question?
Yeah, so what would have been 3,600 times that 0.355?
Let's see what that is. That will probably get us into something. 3.355 times 3,600. We would have had 1278 that you would have tried to break that down. It just gets so confusing when you get there, because now what you have is 1,278 seconds and no minutes. Then you have to go and convert it to seconds. I mean to minutes. Yeah. So that gives us just everything in seconds. Okay? Is that making sense? Yes. Or are we just confusing everybody today? That's okay. Questions are good. Questions are good. If you find an instructor that does not want you to answer questions, do you know what that means? They probably don't know what they're talking about. And I don't say that I know all the answers to the questions, because, y'all, I've been in Calculus 3 somewhere, and I said, okay, let me come back to you next class once I find the answer, because I don't know. It may happen here, too. Who knows? But if an instructor really bucks about you asking questions, then that's a problem. They probably don't fully understand what's going on. So questions are welcomed. They're welcome. Any other questions before we go on? Is there a question back there? No? Okay. If you remember, and we're still talking about this same material here, we talked about radian mode. Y'all remember that? And we drew up the circle, and we said that 1 radian, you know, that angle measured 1 radian if the radius was also equal to that arc length S. Well, we're going to talk a little bit more about that S today. You know, a little bit more about that before we conclude this up and go to another topic. The radian measure formula, theta equals S over R, can be used to measure arc length. How many of us are going on to Calculus 1, 2, and 3? Most of us here. Boy, y'all are going to really see arc length once you get to Calculus 2. You'll be like, oh my goodness, arc length. But it won't be so bad here. This is used to measure arc length along a circle. So S, we can convert this formula. S equals R times theta, where here theta, when dealing with arc length, is specifically measured in radians, okay? So for arc length, you cannot use the degree measure. You must use radian measure. Let's look at an example of finding arc length. Or we may use this to find theta. Find the radian measure of the central angle of a circle of radius 80 kilometers that intercepts an arc length of 160 kilometers. Now, we want to find the radian measure, which means we want to find theta. If they give us radius, which is 80 kilometers, arc length represents, S represents arc length, by the way, that represents 160 kilometers. Now, you have to be careful in these problems because we are finding theta. Theta is S over R. Our units here, they need to be the same, okay? It doesn't matter if we're using meters and meters or feet and feet, kilometers, kilometers, because they're going to cancel out and you're going to get to the same ratio. But these have to be the same in dealing with these problems in order for it to work out right. So we want to find theta. So knowing that theta is S divided by R, S is the arc length, which is given to be what? 160 kilometers. And radius, 80 kilometers, which means we have what? An angle of 2. If it's just 2, it's assumed to be radians, but you may want to, hey, put the little radian there, okay? 2 radians, because we know by this definition that what? This theta that we're dealing with will be measured in radians. So if you put nothing there, it's okay, because it's assumed to be what? Radians. Another example. Let's find the length of the arc on a circle of radius 9 feet intercepted by a central angle of 60 degrees. So you tell me, what do I need to do? Okay, what I need to do, as the young gentleman said, is to convert this 60 degrees into radians, because this whole arc length formula is based on that theta is measured in what? Radians. So how do I convert 60 degrees? What do I multiply by? 180 goes where? On the bottom, because remember, I want to cancel my degrees out. And what goes here? Pi. Remember, pi radians equals 180 degrees. So in essence, I need to simplify 60 over 180, which simplifies to what? 1 over 3. So what I have is an angle pi over 3. So now I have converted my angle into radian mode. I can go about doing the problem. They want us to find the arc length, right? When we have a radius of 9 feet, so knowing that our radius is 9 feet, that means that our arc length will also be measured in what? What unit? Feet. So we need to say whatever feet. So 3 goes into into 9 3 times, so 3 pi feet. That represents my my arc length. Okay? Okay, are there any questions before we shift gears? Any questions before we shift gears to another topic? He said shift away. Okay, I'm ready to shift away. Question? Okay, yes. S stands for arc length. R is the radius. Is that what you wanted? Does that answer the question? Okay, so in the formula, theta equals S over R. Theta is our angle measured in radians. S represents arc length, and R represents radius. Okay? Are there other questions? Okay. Shifting gears here. We're going to look at trigonometric functions. And we're going to look at the unit circle. Okay. We have 6 basic trigonometric functions. And we're going to look at the unit circle to kind of describe these functions, or to define the functions, actually. Excuse me. In the back cover of your book, or on the last page of your book, you should see a page looking like this. And we're going to talk about this unit circle. Excuse me. If you notice, on this unit circle, there are degrees and there are radians. And that tells us the degree of each of those dots there. Let's try to look at this unit circle. By the way, what does the word unit mean? Unit means what? Nobody? Unit means 1. Excuse me. In mathematics, the word units means 1. So when we talk about the unit circle, we're talking about circles that have radius 1. Okay? Circles that have a radius 1. This is important because once we get into talking about, other things, it may not have a radius of 1. But we're going to look at the unit circle, which means we're looking at circles with radius of 1. Now, this is a unit circle, but we can still think about this as what? Quadrant 1, 2, 3, 4. Y'all remember those circles we put up the other day? Not yesterday. But we went around and we said, okay, our quadrant angle, 0, pi over 2, pi, 3 pi over 2. Or 0, 90, 180, 270. Okay? These are still our angles. Since we're dealing with a unit circle, this represents the point 1, 0, right? Unit circle, radius 1. We're on the x-axis, so that's 0. Here, this represents 0, 1. This represents negative 1, 0. And this represents 0, negative 1. Now, we can go through and we can label points. We said from here to there was 1/4 of a revolution. Well, we can break that down even more to where we can have something like pi over 4 or pi over 6. And up here, pi over 3. And these are just a few of the common angles that we have. You know, if we rotate this initial ray and have this line coming out, that'll be our terminal ray. These points also have, or these angles also have points associated with them. If you look at your unit circle, pi over 6, it has a point, square root of 3 over 2, comma, 1/2 associated with it. Okay? It has that point. That's a point on the line. Remember, the equation of a circle is x squared plus y squared equals 1. This is the equation of a circle centered at the origin of radius what? 1. So, at pi over 6, this corresponds to the point on the circle, square root of 3 over 2, comma, 1/2. If we put that in here, we should get a true statement. That should be 1 if we square x and square y. This pi over 4 is associated with the square root of 2 over 2, comma, square root of 2 over 2. Pi over 3 is associated with 1/2 square root of 3 over 2. So if we look in quadrant 1 here, okay, we have, of course, this is the point or the angle 0, and here this represents the angle pi over 2, or 90 degrees. They also have the degrees here too, okay. This is 30 degrees, 45 degrees, 60 degrees, okay. Notice that this is quadrant 1. Remember, in quadrant 1, our x's are positive and our y's are positive. In quadrant 2, the x's are negative and the y's are positive. These quadrants copy each other, okay? If you look at your unit circle, you can see a pattern, can you not? If you look at 2 pi over 3 radians, which represents 120 degrees, the point associated with that has similar coordinates with the points associated with pi over 3. This is the point 2 pi over 3. And the points associated with it, 1/2 square root of 3 over 2. Notice, very similar, but what? Over here, the x's are negative and the y's are what? Positive. And we can continue on. We have over here 3 pi over 4, which corresponds to this pi over 4 here. And the point associated with it is negative square root over 2, square root of 2 over 2. Okay? They correspond. We have a point over here corresponding with pi over 6, and that is 5 pi over 6. So what is this point? Negative square root of 3 over 2, comma, 1/2. So really, if we know that first quadrant, we can get that full circle, can we not? Because what happens in quadrant 3? X and Y, they're both negative, right? Quadrant 4, X is positive, Y is negative. So if we can get one quadrant down, we can get most of these things down. Now I know you're asking yourself, boy, Ms. Bergen, this is a whole lot to remember. And it is, isn't it? He says, no, it's not. I'm thinking about how I'm going to handle this situation. At some point, I'm going to let you use this unit circle. But I may give you a unit circle quiz or something. I don't know. We'll think about that. But at some point, you will have access to this unit circle, okay? You won't have to know it all by heart for every test because this stuff will continue on. Okay, so we can get these points. We can fill out this whole circle if we wanted to, but it really repeats on. And you can refer to your to that page in your book in the back cover. Now, since we know all this, let's define these trigonometric functions. First of all, we're just going to tell you what they are, and then we'll define them based on this unit circle. So, the 6 trigonometric functions are sine, cosine, tangent, cosecant, secant, and cotangent. Okay? Those are our 6 trigonometric functions, and we want to define them based on this circle stuff. Okay? So let's look at a formal definition. Let T be any real number. And let X, comma, Y be a point on the unit circle. Corresponding to T. Then we can define these values, and we're going to use the abbreviation sine T will be the Y coordinate of that point. Okay? Cosine T will be the X coordinate of this point. Tangent T will be Y over X such that X is not 0. Remember, no zeros in the denominator fractions. Cosecant T will be 1 over Y for Y not 0. Secant T will be 1 over X for X not equal 0. And cotangent T will be X over Y for Y not equaling 0. Now, let's notice some things here. Sine and cosecant are called reciprocal functions. Okay? Because what? Cosecant is what? The reciprocal of that what? Y is 1 over Y. Cosine and secant are reciprocal functions, and tangent and cotangent are reciprocal functions. Okay? Which means that if you know one, you can easily find the other. Let's look at an example. Let's find the point, and here we will be referring to that unit circle, so keep that handy. Find the point X, Y on the unit circle that corresponds to T equals pi over 3. So we get our unit circle out. Hey, where's pi over 3? The first quadrant. What is that point associated with it? What's that point X, Y? Okay, 1/2 and square root of 3 over 2. Okay? Nothing too terribly difficult about that. Let's do some evaluating here. Let's evaluate the following. Let's evaluate sine of negative pi over 4, cosine of negative pi over 4, and tangent of negative pi over 4. Well, I need to figure out what is this negative pi over 4 stuff? What does that negative mean? That we are rotating, clockwise. So, and we can look at this unit circle to kind of figure that out. Okay? What we can do to find negative pi over 4 is, if you look at that unit circle, in which this is pi over 4 here, if I go the same distance down, I guess I should have put my points in here. This represents 11 pi over 6. This one represents 7 pi over 4. And this represents 5 pi over 3. But notice, from here, on this unit circle, I have moved 1, 2 dots up. Well, I want to go the same distance down here, so I'm where? 7 pi over 4. So, instead of going pi over 4 here, I'm just going to go in the opposite direction to 7 pi over 4. And if you look on your unit circle, that's a what? Straight line down. Straight line down like that. So, negative pi over 4 corresponds to what? 7 pi over 4 on our on our unit circle. So, which means that in order for me to evaluate, I need to look at 7 pi over 4. So what is sine of 7 pi over 4? Sine represents which coordinate that's associated with that point? It's associated with y. And what's the y coordinate? We didn't even tell us what the point was. What is the point associated with 7 pi over 4? Is it square root of 2 over 2, comma what? Okay? So this means that what? Y is sine. So that's negative square root of 2 over 2. Cosine is represented by what? The x. And what is tangent represented by? Tangent is what? Y over x. Which means what? If we take the reciprocal of the bottom one, we'll get what? Negative 1. Okay? Negative 1. Okay. Any questions so far? Okay, now we're going to shift a little bit, and we're going to talk about the domain and period of the sine and cosine function. Now, we're just going to talk about this today. Later on, we're going to actually form the graph by looking at the domain, the range, and all those things. I think that comes a few class meetings down the road. But we're going to look at the domain and the period. The two most common trigonometric functions are sine and cosine, by the way. You'll probably see that more than what you would see any other thing. Once you get to calculus, you probably see sine and cosine and tangent more than you see the others. Here you will see them all, you know. But they are by far the most common. domain of a function just generally? What's the domain, just generally? Anybody? The domain is the set of values that we can put into the function and get a real number back. Right? All the numbers we can put into a function and bam, out pops a real number. Basically, that's what the domain of a function is. What is the range of a function? We're not going to talk about that, but what's the range? All the values that come out of it. Right? The domain, the values we put into it, or we can put into it, the real numbers that come out represents the range of the function. Okay? Now, the domain of the sine and cosine function is the set of all real numbers. And what that means is that there is no restriction on what we can put into the sine and in the cosine function. No restriction. Anything you put in there, you should get something out. Right? And we know that's not true for all functions. For example, f of x equals 1 over x. What's the domain of that function? All real numbers except x equals 0. Because we cannot put 0 into that function and get a real number back. 1 over 0 is undefined. But the sine and cosine functions, hey, there is no restriction. You can put anything in there and get something back. Now, what do you get back? That's the question, isn't it? What do you get back? Well, the range can be found by going back over here to this unit circle. Go back to this unit circle. The x's represent cosine and the y's represent sine. So if you want to mark on your little paper cosine, theta, comma, sine, theta, then that's okay too. The first value represents cosine, the second value represents sine. Now, in putting all these numbers in here, if you look at the unit circle, sine starts at 0. It goes to 1/2, square root over 2 and 2. It goes all the way around. It goes down to also -1, and it comes right back to 0. So looking at your unit circle, what do you think the range of the sine function will be? It's going to be the numbers between -1 and 1. Right? Because we get a 1 back here too. We get a 1, we get a -1, and everything between. How about cosine? Well, cosine 0 is 1. It starts at 1. It goes on around, and right here is -1, and it starts going back down to 1. So, the range of the sine and cosine function are all values between -1, including -1, and 1, and including 1. So, we do not have a restriction on the domain, but certain values will come out. Now, what this means for us is that, you know what, if I can put every single number into that function and only numbers between -1 and 1 come out, then that means that some of these values would share the same number. Some of these angles would share the same function value, right? And we know that because of coterminal angles, right? We know that there are going to be several angles that have sine 1 or something, you know, or sine theta equaling 1. And when you have functions like this, they are called periodic. Periodic. Okay? They are called periodic functions. So let me see where I want to start writing. I've said a lot of this stuff that I've written. Okay. So, sine and cosine are periodic functions. And what this means, and we will define what a periodic function is in a few minutes, but we want to just explain what it is. What it means for sine periodic is that sine t will equal sine of t plus 2 pi n. And we're going to talk about what that means. Cosine t equals cosine of t plus 2 pi n. Now, going from 0 to 2 pi and find our sine values represents one revolution of the sine graph, okay? Kind of like when we were talking about coterminal angles, adding 2 pi. You can add, subtract 2 pi. Well, I have gone one full revolution when I go from 0 to 2 pi. So when I add 2 pi or any multiple of 2 pi, that's where the n comes in, 2 pi, 4 pi, 6 pi, then that gets me to several revolutions or several periods of this sine function, okay, or the cosine function. So by my adding 2n pi, I'm just adding periods to this sine function. And by the way, it goes on, it's a wave, and it goes on and on and on and on and on and on, okay? So what does it mean for a function to be periodic? Definition: a function f is periodic if there exists a positive real number c such that, abbreviation ST, such that f of t plus c equals f of t. For all t in the domain of f. Okay? So what this means is that, hey, if there is some number out there, c, such that if I add it to that t and I get the exact same value back, then this function is periodic. Does that make sense? This function is periodic. And then the smallest number c, for which all this stuff happens, is called the period of f. So the smallest number c that I can find that will produce for me an equivalent answer to that f of t is called the period of that function. Because it's going to go on and on and on and on and on, but the smallest one gives me the period. Okay, let's look at an example of using the period to evaluate functions. We want to evaluate using the period. For example, cosine 5 pi. Cosine 5 pi. Now, let's talk about this for a minute. We had over there that sine t equals sine t plus 2n pi, right? Which means that 2n pi will be like that c number, right, that we're talking about. The smallest number c. So I need to think about some things. 2n pi. What type of number is 2n pi? 2n pi will be a even number, will it not? Or 2n produces an even number. Let's leave the pi alone for a minute. So if I can get something plus 2n pi, then I can kind of get there, right? Or minus 2n pi. So how can I break up 5 pi as some even pi and something less than that? Does that make sense? Did I state that correctly? How can I break up 5 pi, something pi that's even plus something that's less than that? What is that? Pi plus 4 pi, right? Does that make sense? 5 pi. Because I want something to be 2n pi, which is any even number times pi. And I can do that by 4 pi plus pi. So what does this mean? I have cosine I have cosine t plus 2n pi, and that equals what over there? Cosine t. Right? Do we see that? No. Okay. Let's go back over here.
Well, you wrote cosine pi.
Yeah. Let's.
Cosine t.
Well, here we're dealing with sine t. The t represents an angle. Okay? Let's think about that. So, here our t represents over there 5 pi. Okay? So t is like our 5 pi. Now, we have that cosine t equals cosine t plus 2 pi n. What this is doing is we're breaking this down to where we take out the times that it repeats. Okay? And to do that, 2n produces even numbers. So we need to break 5 pi down as some even numbered with pi associated with it, and something that's less than that even number. It still could be an even number, but it has to be something less. So when we do that, we have 5 pi. We can break it down as pi plus what? 4 pi. So our 4 pi here will represent this 2 pi n, which will take out all of those extra periods. And I'm just going to be left with this first one, which is less than our 4 pi, which is what? Pi. Did I just totally confuse the whole class?
Yes.
Okay, let me think of a way to say this so we won't confuse you. Wait, I want to ask, did somebody get some out of what I said, or are you all lost? Did anybody get something?
I think the graph was a sine function.
Yeah, but you know, at the moment, we are not supposed to know what that is.
That represents the repetition.
It does. It does. And we'll just go ahead and tell you sine function is a wave. And it's going to look something like this. And it keeps going and going and going. So what they want us to do is to evaluate sine 5 pi without a calculator. That's why they're using this period stuff. So this here is one period of the sine function. Now I can go this way. This represents 2 periods. I can go this way, and that represents 3 periods. So I may have 3 periods of this sine function, but what they want me to do is to evaluate sine of a specific value by taking all that repetition out. And knowing that this thing repeats every 2n pi times, we want to take that 2n pi out. All this means is that we have some even number times pi that we need to take out of that 5 pi. So we take it out.
So the n don't represent anything but numbers.
Like 1, 2, 3, 4.
I mean, that's all it means.
Right, 2n. If you think about 2n collectively, just think about that as an even number. An even number times pi, we want to take it out. And from 5 pi we can. Because if we think about 5 pi, that's pi times pi times pi, or plus pi. Pi plus pi. Ooh, plus pi, plus pi, plus pi. And if I want to take out all even, This represents even, this represents even. If I take all that out, I'm left with that pi. Does that help? Does that help? Is that better? It looks a lot easier. But you know what? It looks easier now, but once you start with this negative stuff, then it may not, well, we'll try to make it easy for you then too. But that's what this means. You want to look at all those pi's. We'll try. Hey, I'm willing to try it. Whatever helps you understand, I'm willing to try it. But we want to take all the even portions out, and we're left with cosine pi. What's cosine pi from that unit circle? Huh? You don't know? Unit circle. It's okay, unit circle. Cosine pi. Here's pi here. Cosine represents that x value, and that's what? -1. So cosine pi is -1. Now, I'm sure there's other people here who've not taken trig before either. You'll be okay. Huh? See? You'll be okay. And I do want to put in a plug that y'all, that room right next door to us, 342, there are some excellent guys in there that know stuff all the way to calculus and trigonometry, and they will help you. They are paid to help you, and it is a free service to you. All right, y'all. Are we ready to try another one? We got to. We can't call it a day. That's right. Let me see which one I want to do. Let's look at, and let's just go over here since we might need more space. Let's look at sine of 9 pi over 4. Now let's see how we want to break this down, because we want, again, our 2 pi's. And this 4 out here, you know, let's break this down into where, and we'll just take the sign out of it. Let's just look at 9 pi over 4. 9 pi over 4 is the same as what? 2, let me see how we want to do this. Because we need something. With what? No, ask the question again.
If you take all the even components out of 9, would that be less?
But we have this 4. We have this 4, and that's going to pose something different for us. It's a little different than 5 pi. Because what we want is, and as I said, that's plus 2n pi, and can represent negative numbers, just as long as it's even. So it can be t minus 2 pi n, okay? We need something. Okay, so let's look at 9 pi over 4. If we take out pi over 4, well, no, you can't do that. Well, yes, you can. What will give me, what can I add or subtract from that to give me 9 pi over 4? 8 pi over 4. Okay, there you go. Now, why did I choose 8 pi over 4? Because this gives me some what? Even. In fact, I did this differently in my notes. But this gives me some what? Even power of pi.
Oh, that's be. Oh, that's be.
Even. Dealing with sine and cosine, yes.
So could you break it down into pi over 4 plus 4 pi over 4 plus?
Well, no. Wait. It has to equal, always has to equal 9 pi over 4, though.
Okay.
It has to equal 9 pi over 4. Now, what I have in my notes, I have pi over 4 minus 4 pi, which is equivalent, but it's hard to think about. So we want to do what's easiest for you. This gives me my 2n pi, doesn't it? So this is equivalent to sine pi over 4. And what is that from our unit circle? Sine pi over 4? And you will become very accustomed. You will learn that first quadrant. Those common angles, you'll know that sine and cosine like the back of your hand before too long.
also know that it's, like it's a full rotation, and you're just going back to,
Because this is a full rotation. This 2 pi means one full rotation. If this was 4 pi, it'd be 2, and then whatever's left over. Okay? Okay, y'all, we're going to move to something else. Even and odd functions. Even and odd functions. You should have talked about this in Math 112, I think, right? Okay, yay, we have something that sounds familiar. Something that sounds familiar. Even and odd trig functions. Okay. Cosine and secant are even. And what that means is that cosine of negative t equals cosine t, and secant of negative t equals secant t, right? Even means if I put the negative of that value into that function, then out will pop what? That positive value, okay? If I put in negative t, it's the same as putting in t. Doesn't matter at all. My odd functions, all the rest of them are odd. Sine of negative t is negative sine t. So if I put negative t into the sine function, then out, what will happen is it will make the whole function negative. Tangent is a negative function. Cotangent is negative. Okay? So, they may want us to evaluate some functions using this idea of even and odd. So, for example, if we are given that sine of negative t is 3/8, then we want to find sine t and cosecant t by using the definitions for even and odd. So, if I know that sine negative t is 3/8, then what is sine t? What is sine t? Oh, excuse me, positive 3/8. What's sine t? What's that mean? Okay? Sine of negative t is negative of that value. Negative of what comes out from that. So that's negative 3/8. Does that make sense? What's cosecant? Well, here we're using something different. We're using that cosecant and sine are what? Reciprocal functions. And that means we take the reciprocal, which is negative 8/3. Okay? Reciprocal functions. Now, remember that from a few minutes ago? Another example. Suppose we're given that cosine t is negative 3/4. And we want to find cosine of negative t and secant of negative t. Well, cosine is an even function, which means the cosine negative t is the same as cosine t. Cosine t is negative 3/4. They're the same thing, negative 3/4. And what's secant? Secant is a reciprocal function of cosine, so that's negative 4 over what? Negative 4/3. Okay? How many of us brought our calculators today? Good. We're going to do a few calculator examples. Just to know that, hey, I know how to work my calculator and I know how to get in degree and radian mode. Did you figure out how to get in degree and radian mode already?
I don't have one yet. Is that supposed to be negative 3/4 of that A exactly?
Because the cosine of negative t is the exact same thing as cosine t.
Oh, that's right.
No problem. Okay, so just a few calculator examples. Tangent pi over 3. Do we know how to get that into radian mode, our calculators? No. And I may not know either. Depending on what kind of calculator you have. Who said no? Nobody said no? And this is an example. Pi, this will be approximate, by the way. Pi, you should have a pi button on your calculator. Should have a TAN button. Pi over 3. Some calculations have to do tangent, open parentheses, pi divided by 3, close parentheses, equal. Some of you have to do pi divided by 3 and then tangent. Depends on your calculator. So, are we getting 1.7321 when we do that? Are we getting that? Nope. Let's see.
Because I did tangent
Okay, then you need to do pi
divided by 3, right?
and then close, yeah, equals. Is that not what? Maybe I wrote the wrong thing. What, are y'all getting that or y'all getting 1 point? In radians. Is this thing in radians? I don't know. You got one of these calculators, I may not know how to, I don't know. It is. I don't know, you still have your book for this thing?
Nope. I bought it off eBay.
You bought it off eBay? Well, I can't help you with that one. Somebody else later after class can help her with the TI-83, the old kind. I don't know. But everybody was getting this. It could be in degree mode, and it's some menu you have to go under. We'll work with it after class, okay? Cotangent 1, you may have to do what? Some of you may have a cotangent button. Some of you may not have a cotangent button. But that's 1 over tangent, and you should get 0.6421. Did you get that? What? No, yes? Not yet, okay? This is just to make sure we know how to work our calculators. Cosine of negative 2.5, see if you get what we have on the board. Negative 0.8011. Did we get it? Yes, no, I'm working. No, did anybody get it? Yes, you got all of them. Okay, what did you not get? Let's see here.
I don't have a cotangent, but
Okay, you got to do 1 divided by tangent then. Remember their reciprocal function, 1 divided by tangent of 1. See what you get there. Okay, so are we okay with the calculators? If not, we'll try to help you after class. Okay, so we will see you on next class talking about another topic, okay?